All right. Our next topic is the discrete time version of the Laplace transform. So let's remember what we did. We did this from j omega. We put a real part to this and say that it's now sigma plus j omega. And we called it something new as a variable, and we call it S. So it has a real part and an imaginary part. And then now all we have to do is to see what's happening to e to the j omega, because as you may remember in the Fourier transform, we were using capital X of e to the j omega as the Fourier transform expression, and everything is 2 pi periodic, etc. So e to the j omega becomes e to the, in parentheses, sigma plus j omega, right? And that is equal to e to the sigma times e to the j omega. Now, e to the sigma is, or it can be considered as now our new variable. We can denote this to be r. So I'm going to write it like r times e to the j omega. And the reason that I am calling it to be r is it comes from the radius. What is the magnitude of e to the j omega when r is equal to 1? What is the absolute value, the magnitude of e to the j omega, which is a complex number? But e to the j omega is actually a circle on the complex plane, with the horizontal axis being real, vertical axis being imaginary. So this is the real and this is the imaginary part. E to the j omega is actually one full rotation. As omega traces from 0 to 2 pi, it makes one full circle. And that's why e to the j 2 pi is equal to e to the j 0, which is equal to 1, by the way. At real 1, you reach a real value. But for all other omega values, the magnitude is always 1. Why is that? Because e to the j omega is equal to cosine omega plus j sine omega. And the magnitude of e to the j omega is equal to square root of cosine square omega plus sine square omega. And we know that this is equal to 1, right? So the situation is quite simple, I guess. Now, if you multiply anything with e to the j omega, now it becomes another circle, but now it's from, let's say, a value of r, and it makes one full rotation. And at omega is equal to 2 pi, it comes back. And this is the radius r that we have. For the black circle, we are going to call it the unit circle because its radius is equal to 1. For the red one, it is just r times e to the j omega. But that's not all. It's not the only thing that we will do. R is like our new sigma. Okay, it's actually e to the sigma. So that's our new additional variable. Omega was already there. With the addition of a new variable, it will make an even more complicated expression, r times e to the j omega now. So we have to reduce it into a simple form, just like saying that sigma plus j omega is equal to S. R times e to the j omega will be called Z. Okay. So we will just notate it by Z. And the transform by using a certain value of, or a free value of R will be called the Z transform. Instead of the discrete time Fourier transform, we will shrink down the expression to become the Z transform. But what is the Z transform? The Z transform is actually like this. You may remember the discrete time Fourier transform. What was it? The discrete time Fourier transform, let's remember that one, that it's critical, was already equal to a summation n from minus infinity to infinity, x of n times e to the minus j omega n. You remember this? It's the discrete time Fourier transform. Now the z transform is the replacement of e to the j omega with z. So we will replace e to the j omega with z. Where is e to the j omega in this expression? E to the j omega is here, but it is e to the minus j omega. And it is e to the minus j omega times n. So what is then the z transform? How can we substitute e to the j omega with z, and what does it make? It makes x of z, of course, summation n from minus infinity to infinity, x of n, z to the minus n. Right? This is the formula for the z transform, which is pretty much the same as the formula for the discrete time Fourier transform. So if you remember one of them, you will automatically remember the other. Before going into any further examples, I will give you a very critical hint about the z transform. And it's actually better than the Fourier transform. It's not even a transform. It's the representation of a discrete time signal. And can you see it? Or how come? What do I mean by it's the representation of a signal? Now let's think of an x of n, which is like a discrete time signal, as we know. It's equal to, let's say, 2 at 0, 1 at 1, and 3 at 2, and minus 1 at 3. Okay, this is just some example x of n. You can draw it like this, or you can write it like all the others I will assume to be zeros, like this. The only non-zero support of the system signal is this. It's a length 4 signal. We can write it like x of n is equal to 2 when n is equal to 0, 1 when n is equal to 1, 3 when n is equal to 2, minus 1 when n is equal to 3, and 0 else for all other n values. You can write it like this. It's not very analytical way of doing it, but you can also plot it, and there's no other way. It's just the signal itself, and I'm representing it like this. Now the representation using the z transform is an interesting thing. Just focus to the expression that we see here. We have every x of n, so every value of x of n is multiplied by the corresponding z to the minus n. For instance, x of 0 is multiplied by z to the 0, which is actually 1. And then we have x of 1 at n is equal to 1. This makes x of 1 is multiplied by z to the minus 1. X of 2 is multiplied by z to the minus 2, etc. And then they are summed up. They are added, combined. So would we agree that x of z, which is the z transform of this particular signal, by the way, is quite simply equal to 2 times z to the 0, which is 1, so we have 2, plus, for this one, 1 times z to the minus 1. So it is z to the minus 1, or 1 times z to the minus 1. You can put it like this. Plus 3 times z to the minus 2, because at 2, when n is equal to 2, z to the minus n becomes z to the minus 2, and x of 2 is 3. Plus, or actually it's a minus because there is a minus 1 times z to the minus 3. At 3, the value is minus 1, so it's minus 1 times z to the minus 3. Let me just write it in a more compact way. 2 plus z to the minus 1 plus 3 z to the minus 2 minus, I will still, well, that's not right, minus 1 minus z to the minus 3. Now, if I give you this z transform as x of z, just by looking at this x of z, you see the signal itself, the values of the signal. What are they? They are 2, 1, 3, and minus 1. The others are plus 0 times z to the minus 4, plus 0 times z to the minus 5, etc. And do we know the locations of this 2, 1, 3, and minus 1? Where are they? This one is at 2 is at z to the 0, so it's at 0. 2 at 0. 1 at 1, z to the minus n, therefore z to the minus 1 means n is equal to 1. 3 at 2, and minus 1 at 3. So it shows the signal itself. The signal is transformed, the coefficients of the signal are transformed into a polynomial representation, a polynomial of z now. And that is a very typical way of making a representation. For example, in computer programming, how do you make a discrete time signal? You can put it in an array. That is the convenient way of doing it. Like you allocate some memory and assign it to become an array, and the value at the 0 index will be 2. At index 1, it will be 1. At index 2, it will be 3, etc. That will be an array. But in mathematics, maybe a more or a better way of making a representation is not writing it in the form of an array, but writing it in the form of a polynomial like this, a z polynomial. Now, I will ask you some questions, some extensions of these questions to as a check whether you have understood it well or not. If I, oh, by the way, I seem to have made a mistake. This is not a capital X of S, it's capital X of Z, of course. We are not in the Laplace transform. Now we are doing Z transform. Sorry about the mistake. The question is as follows. I give you X of Z as something, let's say 2Z plus Z to the minus 1 plus 3Z to the minus 2. So this is my Z polynomial. Is it a Z polynomial? The answer is yes. And what is the signal then? This is X of Z, capital X of Z. So what is X of n? Or can we plot X of n? And the answer is a big yes. This part, these two coefficients, we already know how to handle them. There is a 1 at n is equal to 1, and there is a 3 at n is equal to 2. But how about this? What does it mean? Notice that in the Laplace transform, we have x of n times z to the minus n. So when n is equal to minus 1, z to the minus n becomes z to the 1. So actually, z by itself means n is equal to minus 1. If it is z square, maybe I should expand it a little bit further to make a more meaningful example. Plus z square, let me say. So this is x of z. So when you have, sorry, z square it means z to the minus n at n is equal to -2. So at n is equal to -2, its coefficient is 1 here. At n is equal to -1, z to the minus of -1 is z. The coefficient is 2. And the others are at positive n's. This 1 is at n is equal to 1. This 3 is at n is equal to 2. Okay, so the signal is essentially at n is equal to -1, we have 2. So this is x of n that I'm just plotting at -1. It's equal to 1 at -2, because this is 1 times z squared. And it is equal to 1 at n is equal to 1. And it's equal to 3 at n is equal to 3. So this is my signal. What are the other values? The other values are just 0, including, for example, n is equal to 0. I don't see any constant term in this x of z expression. There is no +5, for example. If there is a +5, it means +5 times z to the 0. So the value at 0 will be equal to 5. But I don't see any numerical term, standalone numerical term in this x of z. So of course, then at 0, the value is 0 because it doesn't appear. So it must be 0. And the others are also 0. So this is x of n. Okay, this is what the z transform is. It is the representation of the signal in a z polynomial. It's the representation of the discrete time signal as a z polynomial. And the z powers could be positive and negative. If the z powers are negative, like z to the minus k, the location is at k. So if it is z to the minus 3, for example, it means at n is equal to 3. So positive sides, the positive n values, are notated by these negative z powers. So for n is equal to 1 and n is equal to 2, for instance, this is what we have. And when z powers are positive, like z squared, z cubed, z to the 4, z to the 5, etc., they correspond to locations at n is equal to -1, n is equal to -2, -3, -4. So the left-hand sided n values are related with positive z powers, and right-hand sided n values, positive n values, in other words, are related by negative z powers in the z polynomial. These are these two, and these negative powers are here, okay, at the positive and the negative side. So that's what it is. And it also gives you a few more hints about how we can use the z polynomial or the z transform as a system response. This is something that we will see a little bit later, but I want to show it to you now, which is already a property of convolution versus multiplication. Because we know that if you convolve two signals in time domain, you multiply in the transform domain. It may be a Fourier transform, it may be a Laplace transform, and including the Z transform too. So suppose that x of n is equal to 2 delta n plus 1 plus delta n plus 3 delta n minus 1. Now I'm writing it deliberately like this instead of plotting it, so that you must get accustomed to this kind of a representation too. This is x of n, which is 2, value 2 at -1. The value is 1 at 0, and it's equal to 3 at 1. X of n is like this. It's consisting of 2 unit samples. And h of n is equal to 2 delta n plus delta n minus 1, which could be plotted as value 2 at 0 and 1 at 1 on the n-axis. So this is h of n. What is y of n? The output of the system, which must be the convolution of x of n and h of n. Do you know how to make or how to perform the convolution? You fold around one of them. It could be h of n or x of n. You fold and then slide over the other one. And the intersections or the corresponding locations are value-wise multiplied and summed up, accumulated. That's the cumbersome operation of convolution. Now, I'm telling you that y of z is equal to x of z times h of z. Okay? It's the property that we will definitely discover. That's what happens in all of the transforms that we are seeing, which is, so what is x of z? Let's write x of z. X of z is 2z plus 1 plus 3z to the minus 1. Do you all agree with this one? I just took the z transform of x of n, value by value. 2 delta n plus 1 is an impulse at -1. Its value is 2, and therefore its z transform is 2z to the minus 1. Is equal to 0. It is 1 because there's a n, and f is equal, which makes 3z to the minus 1. So this is z. H of z is 2 z to the 1 times z to the minus z, the z transform of expression that I will show. Let me wait. Yeah, the z transform of this expression. So I have two z polynomials, x of z and h of z. Let's multiply those z polynomials. Can we multiply it? Yeah, it's not very easy. You have to be very careful about the multiplications because term by term, you have to just multiply, for example, this 2z with this and then with this. Then you have to multiply this 1 by this and this. And finally, you have to multiply 3z inverse by this and this. And you have to sum up and simplify. Be careful. The common z terms, z power terms, must be combined all together. That's what makes it a little bit difficult, let's say, for multiplying these two polynomials. But when you do that, it will be probably like 4z plus 2z times z to the, this 2z times z to the minus 1 will give you a 2. Okay, it will give you an isolated 2. And then 2 times 1 will also be 2. So those two values of 2 will be added to become 4. Okay, I'm just simplifying the expression already. Was that a question or okay? And then what else do we have? This 1 times z to the minus 1. The last one is here is minus 1, okay? Don't get confused about that. So 1 times z to the minus 1 is z to the minus 1. There is also a 3z to the minus 1 times 2, which makes 6z to the minus 1. There is one more, so it makes 7z to the minus 1. And finally, 3z to the minus 1 and z to the minus 1 are multiplied to give you 3z to the minus 2. And there's only a single such term. Okay, and if you plot this polynomial in the time domain, this is y of z. The corresponding y of n will be like this. It will be 4 at minus 1. It will be 4 at 0. Is there a question? Is there a question? I heard something, but anyway. It's 7 at z is equal to 1. Z is equal to 1, and there's a 3 at 2. So this must be the output of the convolution of this and this. Just try to convolve them. Try to convolve them and see if you can really get this one. That would be a nice exercise for you. It must give you the same thing. So, in short, or in practice, convolution is equivalent to polynomial multiplication. So if you're uncomfortable with the convolution formula, like folding around and sliding, if you're not very much comfortable with yourselves in doing that thing, then you could also just convert it into a polynomial form, into two polynomial forms, and try to multiply two polynomials. But I don't think multiplying polynomials or convolving signals are, one of them is more difficult than the other one or anything, okay? They are equally difficult. In fact, if you want to write the program, the computational algorithm of this operation, I think for the computer, convolution is an easier thing. You can write a convolution algorithm as a C function, as a MATLAB function or whatever. Of course, it already exists in such, in a lot of libraries of these programming languages, but you can also do that. Convolution can be programmed, it's manageable. But on the contrary, multiplication of two polynomials is a tricky programming. And it was a programming homework or a project when I was a first year freshman student in the university. So they were teaching us the programming languages like C. In the old days, we were learning Pascal programming, but it's the same. So using Pascal language, the professor asked us to write a program that multiplies two polynomials that are represented in a kind of representation. And the representation is in the form of an array, where the first coefficient will correspond to the constant. The second one is like x to the power 1. The other one will be x to the power 2, etc. So it's in the form of an array, but it corresponds to a polynomial. And there is another array corresponding to another polynomial. How do you multiply these two polynomials, which is the thing that I was trying to do here. And it was very difficult. It took me a week to develop a program which multiplies two polynomials, because common terms should be merged together, and there may be, as it gets longer and longer, more and more common terms start appearing, and it becomes even more complicated. So I was thinking, how am I gonna do that? And it was very difficult. I did it, but I suffered a lot because I didn't know convolution. But if I only knew that it actually corresponds to the convolution of those two arrays, probably I would write the convolution program of those two arrays in an easier manner. Okay, so convolution is polynomial multiplication. The polynomial is the Z transform, and it is just the same as the representation itself. The Z transform is the signal itself. It's there. If you look at the Z transform, you see the signal. Unlike the Laplace transform or the Fourier transform, where when you look at the Fourier transform, you don't really see the signal, but you can, of course, guess what the signal is by just taking the inverse Fourier transform or the inverse Laplace transform. But in the Z transform, the signal is there. You see them coefficient by coefficient, except let's do an example. Except the infinite extents, but though even those infinite extents are essentially the power series combinations. I will show you what it means. Let's say that x of n is equal to a to the n u of n. And the question is, what is the Z transform? From the things that I have shown you before at the top, I can say that x of z is a to the 0 times z to the minus 0, which is 1 plus, okay? When z is equal to, or when n is equal to 1, it means a to the 1 times z to the minus 1. So it is plus a z to the minus 1 plus a square z to the minus 2, because when n is equal to 2, a to the n is a to the 2, and z to the minus 2 is there as the Z transform, plus a to the 3 z to the minus 3, plus a to the 4 z to the minus 4, plus it goes on forever. This is the Z transform, and I know it. But is it possible to make it in a more compact form? Because what I have written is essentially this summation. I have written n from minus infinity to infinity x of n z to the minus n as summation from minus infinity to infinity a to the n u of n z to the minus n. This is the formal definition of the Z transform that I'm writing. And that is equal to n from 0 to infinity. Why? Because there is a u of n here. Therefore, it forces the summation. That's why it starts from 0 to infinity n. I have a to the n, z to the minus n. Now, this is also equal to summation n from 0 to infinity. By the way, I can see that this, the other one is just term by term definition. Or the so the summation to the power n. Are you still with me? Can you hear me? Or is there a problem? There is a problem. I will have to change the problem. problem. The internet is too slow. I'm sorry about that, but I have to continue anyway. So let's not get distracted. The eventual summation is the thing that I write over there, is the last thing. Now, this is a power series sum that we have a times z to the minus 1 altogether to the power n. So let's call this thing, I don't know, let's call it B, okay? Then let me write it in red. It's n from 0 to infinity, b to the n. Do you know what this summation is? If b is less than 1 in magnitude, if the summation converges, this is equal to, yes, 1 over 1 minus b. Exactly. So the top one, which is one of the summation az inverse to the power n, will be 1 over 1 minus az inverse. Okay, do we all agree with this? So instead of this explicit open way of writing the summation, I can equally write it as 1 over 1 minus az inverse. That's the only difference of this question, because we are essentially asking for this kind of a compact expression of a z function. It's not in the form of a z polynomial anymore. It's in the form of a ratio. More similar to the Laplace transforms that we have seen before, right? Because in the Laplace transforms, the expressions were also similar to this compact form. But there is a condition on this one. Let me write it in a different color. There is a condition. The condition is that it must converge. What is that convergence condition? This b, the red b here, must be between -1 and +1. It must be less than 1 in magnitude. Otherwise, this series summation will diverge to infinity, as you see, as n goes to infinity. Condition is therefore b, which is a times z inverse, must be less than 1 in magnitude. Okay, and this is equivalent to a times z inverse less than 1 in magnitude can be rewritten as z, the magnitude of z is greater than the magnitude of a. Because when z is more than a z inverse is like a over z. So if z is greater than a over z is less than 1 in magnitude, okay? So this is the equivalent. Z magnitude is greater than a, which is also further equivalent to saying this. What is the magnitude of z? According to the terminology that we used before at the top of this class. Look at z here. It will make this. So what is the magnitude of Z? Do you have any answer to this? No. Doğukan says 1. It may be equal to 1 if Z is equal to e to the j omega. Yes, now it's more correct, Hasan. It's not e to the j omega anymore. It's r times e to the j omega. Therefore, the magnitude of Z is r, the radius. Let's come back and say that r is greater than absolute value of a. So this is the radius, and overall it gives us another way of representing a so-called region of convergence. Again, just like the Laplace transform region of convergence. What was the Laplace transform region of convergence? It was a dashed line, and to the right of it, to the left of it, or between two dashed lines, right? Now it's a little bit different. We have, again, the complex plane consisting of the real part and the imaginary part again. And then there is a constraint like this telling me that the radius must be greater than absolute value of A. What is A? A is a point here. I will put it as a cross. Does it give you an idea about what it means? What does a cross mean in the Laplace S-plane or the complex plane? Yes, it corresponds to a pole, right? Now, do you see that Z is equal to A is a pole? Because if Z is equal to A, it means it's A times A to the minus 1, which makes 1 here. And there's a 1 minus 1 in the denominator, making a 0 in the denominator, which is 1 over 0, which is blowing up to infinity. And that's why Z is equal to A is a pole of this expression. So that's why I put a cross there. It's actually a pole. And I will draw a circular dashed curve like this, as good as possible. Sorry for the inaccuracy. It must be completely circular, of course. And the region of convergence is saying me that the radius is greater than this value, the absolute value of A, which means the region of convergence is like the outside of this circle. Any circle with a radius larger than, radius is equal to A. Sorry about this. Anything with a radius, any circle with a radius greater than this A will be a valid solution of this R is greater than A. So this yellowish orange like lines will correspond to the region of convergence. Region of convergence for the existence of the Z transform. So the region of convergence is R is greater than A, or absolute value of Z is greater than A. It's if A could also be negative. For example, let's say A is equal to minus 0.5. Then the position, the location of A will not be here anymore. It will be somewhere here, okay, the negative of it. And but the radius will still be the same. That's why we are saying that absolute value of a Z, absolute value of Z, or magnitude of Z is greater than the magnitude of A. There could be a pole at this point, as I indicate with the red dot here, and still the same circle will appear as the boundary of the region of convergence, and out of it will be the region of convergence. It doesn't really depend on the sign of A. It depends only on the magnitude of A, because it defines a radius starting from the origin all the way towards here, or even some imaginary places like this pole here or this pole here. It can be. They will all contribute as the same region of convergence, the same circle, and out of that circle is the region of convergence. And the Laplace transform, the Z transform is therefore this. This is x of z. And the region of convergence is this. So together with the expression of x of z and the region of convergence, these two entities define the Z transform. The Z transform must always be accompanied by the region of convergence, just like the Laplace transform. We're not settled with x of s, capital X of s. You have to also indicate the region of convergence. Remember that. Here it's the same. You have to tell me the region of convergence. And why is it necessary? It's because of the second example that we will see, which is this. X of n is equal to minus a to the power n, u of minus n, an ugly one, sorry, minus n minus 1. It looks awkward, but u of minus n minus 1 is a left-hand sided u unit step. It's telling me that this signal exists from n from minus infinity to minus 1. It's not from 0 to infinity, but it's from minus infinity to minus 1. So it's the left-hand sided signal, in other words. And you may already guess the answer here, which is telling us that it looks like the opposite solution in the Laplace transform, which was telling me minus a to the t u of minus t or something like that, right? Which gave us the same, exactly the same Laplace transform. Sorry, e to the minus at, minus e to the minus at u of minus t. You remember that? It was giving me the same Laplace transform. Now the Z transform of this one is what is it? It is the negative, because of the minus sign of minus a to the power n, negative of summation n from minus infinity to minus 1, a to the n, z to the minus n, which could be converted to a positive index summation by a change of variables. Let's say m is equal to minus n or something like that. With this kind of a replacement of variables, it's also equal to, this time from 1 to infinity, but a to the minus n z to the n, okay? The same summation. And this summation is equal to 1 minus n from 0 to infinity, a to the minus n z to the n, which is a to the minus 1 times z to the altogether to the power n, which is equal to 1 minus 1 over 1 minus a to the minus 1 times z. That simple series sum formula, again, calling that a to the minus 1 times z is equal to b, you will get this. And that is equal to 1 over 1 minus a z inverse. If you do the mathematics, you will see that, which is exactly the same as this. So the Z transform of this signal is also equal to the same thing. And that makes a headache, because then the inverse Z transform becomes ambiguous. We don't know which inverse is the correct inverse. But of course, we have to define also the region of convergence. And from the region of convergence, we will decide which time signal is the correct time signal. Is it this one or this one? If the region of convergence is the radius is greater than magnitude of A out of the pole, the circle defined by the pole, then it will correspond to this. Because out of a circle will correspond to right-hand sided signals. Whereas for this one, the region of convergence will be, by the way, the pole is, since the Z transform is the same, the pole is the same at A, and there will be the same circle, but this time the region of convergence will be inside the circle, which is a disk shape here, and that will be the region of convergence. What is the region of convergence then? It is the radius, which is the magnitude of Z, is this time less than magnitude of A. This pole must be excluded. That's why I'm putting dashed line here. It does not exist inside the set. It's excluded from the set, both at the top and at the bottom. But is it also possible to see that Z is less than A is the region of convergence, or the radius less than A is the region of convergence, by directly looking at the problem itself? And the answer is a big yes, because look at, I want you to focus to here, to this expression. And inside here, I have a B term, and from 0 to infinity, B to the power N. So B must be less than 1 in magnitude. What is B? It is Z over A. A to the minus 1 times Z is Z over A, right? So Z over A must be less than 1 in magnitude. From here, Z over A must be less than 1 in magnitude, which tells me that Z must be less than magnitude of A. This time, Z must be small. The magnitude of Z, which is the radius, in other words, must be less than A. That is the whole difference. So the Z transform overall consists of X of Z, which is the same as the top X of Z, and the region of convergence. But since this is a left-hand sided signal, the region of convergence is to the inside of the circle. If it's a right-hand sided signal, it's to the out of the circle. So things are very similar to the Laplace transform. Let's remember what the Laplace transform says. If the signal is right-hand sided, then the region of convergence is to the right of a line, a dashed line, okay? Right-hand side is the region of convergence. If the signal is left-hand sided, the region of convergence is also to the right of the line, to the left of the line. This time, it's out of a circle for the right-hand sided signal and into the circle for the left-hand sided signals. And just like the Laplace transform case, the inversion, the inverse Z transform is a difficult concept, and we usually invert by trying to write the expression in terms of a Z polynomial. If you can convert everything into a Z polynomial, then it means that you found the signal, because the signal values are there, the polynomial coefficients. But for instance, this one is not a Z polynomial. It is 1 over a Z polynomial, which is not a Z polynomial, but it can be converted. You can divide 1 by 1 minus a Z inverse. So you have to divide 1 by 1 minus Z inverse. And interestingly, when you do that in a proper way, you will find an infinite extent Z polynomial. It is called a long division. We will also see that, by the way. And that long division will give you the signal. But otherwise, the second alternative, which is the correct alternative, is to know the inverse Z transform. You have to have a table in your hands telling you that the Z transform of this is this with this region of convergence. So when you look at your table and if you encounter a Z transform telling you that it's like this, then if the region of convergence is to the out of a circle, you will say that, oops, it's here. The signal must be like this. You just give this answer immediately. Conversely, if the same Z transform expression is valid, X of Z expression is valid here with a different region of convergence, this time into the circle, then you have to just tell me the answer that X of n is therefore this. You should better, therefore, know the Z transform equations. You have to have some tables of typical Z transform pairs. If you don't have it, then the alternatives are a little bit more difficult. Like you have to convert this into a Z polynomial and things like that, which is somehow a little bit more difficult. Now, the last thing that I want to talk about for today, we will continue on Wednesday, is the following. It's about the existence of the Fourier transform itself. It all depends on what the value of A is. Let's go back to the original signal. X of n is equal to a to the power n u of n, okay? We know that if A is greater than 1, or magnitude of A, in other words, is greater than 1, then the Fourier transform does not exist because it violates the Dirichlet conditions. It will be an increasing exponential. A to the n as A greater than 1 will be an increasing exponential, and therefore its Fourier transform does not converge. And if A is greater than 1, then the region of convergence is telling me also that A is here, a pole, and it's greater than 1. And the region of convergence is to the outside of this circle. And there is also a point which is equal to 1, and there's a circle with a radius equal to unity. This orange thing is a unit circle. It may be faint, but I'm also reading it. I wrote unit circle. So this unit circle, as you see, is not in the region of convergence because the region of convergence is to the out of A, and A is greater than 1. Therefore, that region of convergence does not include the unit circle. Region of convergence does not include the unit circle, the one circle. That's why we don't have a Fourier transform. And if this is a system, if this is not x of n, but if it is h of n, you can call it h of n, then it means that the system is unstable because, again, the unit circle is not included in the region of convergence. So just like the Laplace transform, the check for stability or convergence is simple. You have to check if the unit circle is included in region of convergence or not. You have to make this check. If the unit circle is included in the region of convergence somehow, then it means that the Fourier transform exists. Or if it's a system h of n, then it means that the system is stable. This argument, check if the unit circle is included in the region of convergence or not, is equivalent to the Laplace transform of check if j omega axis is included in region of convergence or not for the Laplace. This is for the z. The other one is for the Laplace. Because j omega axis means sigma is equal to 0 and e to the sigma becomes e to the 0, which is 1. So r is equal to 1 means it's equivalent to sigma is equal to 0 case. A radius of 1, that is the unit circle, is actually, that orange circle that I have drawn is essentially the j omega axis of the Laplace transform. And it must be included in the region of convergence for stability or for convergence of the series and all those things. But as you see from this example, even though the Fourier transform does not exist, I told you that the Fourier transform does not exist, the Z transform still exists, and the Z transform is still 1 over 1 minus AZ inverse. This is X of Z. It exists, but for all Z values with a magnitude that are greater than A. So you have to choose a radius, Z magnitude, that is greater than A. You must travel around this region of convergence, which is out of a circle. So Z transform is a generalized version of the discrete Fourier transform. And even for unstable or non-convergent series, you may still have the Z transform expression, which is like this. But the region of convergence is Z, magnitude of Z is greater than A, maybe. It may be that we will continue with several more examples, but the generic way of putting the Z transform is like this. And I hope equating these two or finding the similarity between these two, finding the similarity of regions of convergences where it must include the j omega axis or the unit circle are equivalent things. You must all make sure that you're understanding these. If you understand these things, the other examples that we will see on Wednesday will make better sense and you will better understand the Z transform. And it's easy. It's not very difficult because it does not require integrals, it requires summations, and usually I think the students find summations even easier than the integrals. So this is the topic that we started, the last topic that we will be discussing throughout this semester, which is the Z transform as we have started. And now I will stop the record. And before that, maybe I should ask if you have any questions. I may give you a few seconds in case you may have a question. On Wednesday, we do have a class, if that may be a question. So I don't encounter any questions from the chat, so I will stop at this point. Let's meet on Wednesday. See you until then.